Hello everyone, I'm back with another video. Today we'll be discussing differential equations. It's a pretty easy topic, to be honest. Really, we're not going to be dealing with the hard stuff that you probably do in university. We're going to be dealing with pretty easy. It's kind of like integration and sometimes differentiation. But basically, the premise of this topic is that a differential equation is an equation that expresses a relationship between a function and its rate of change. So you might have a function like, I guess, y equals whatever, f of x, who cares? And then you might have another equation which says dy dx plus 3y equals x, right? Whatever this means. It's basically just an equation. It's got a derivative in there. It's got the original function and it's got an independent variable. It doesn't always have to have an independent variable. Sometimes it could just have y's and dy dx's. It doesn't also have to have just a dy dx. It could have d squared y on dx squared, or it could have the third derivative or the fourth derivative. It could even have multiple. Okay. There are many, many different types of differentials. We'll only kind of be dealing with easy first order linear differentials, which is something I'll talk about in a moment. But really, this is quite important. It comes up a lot of the time. One of the things that is covered, not in this topic, is simple harmonic motion. Simple harmonic motion is basically a model that I guess describes how particles move up or down between a center, or they oscillate around a center, and that has a particular differential equation. I think the differential equation for that is d squared x on dt squared equals minus n squared x. Okay, so it's something about they're telling us the second derivative of x is actually equal to minus n squared x. Okay, so this is what we will be dealing with. Nice. So in terms of notation, okay, the notation that we have to keep in mind is that when we might have a dy dx, then d squared y on dx squared, and then you would also have d cubed y on dx cubed. But we sort of start not getting bothered with this, and you end up writing it maybe as dnx on dxn. People often write these also as y dash, y double dash, and then triple dash is sort of where we sort of like draw the line, and y4. And then if you have the derivatives with respect to time, for example, like displacement with respect to time and stuff like that, we often denote it with y dot, y double dot, and do we do triple dot? This is kind of wild if we do anything more than triple dot. Bro. Yeah, okay. I don't think we do triple dot. At least I don't know the reasoning for why we would bother. But there's that. So that's our type of notation. And I might just put in here only for derivatives with respect to time. Perfect. So now let's talk about the order of a differential. So this is just an important, I guess, term that you have to keep in mind. This is I guess you could say the order of a differential is the order of the highest derivative present. So it's the order of the highest derivative present. Okay, so if you have a first derivative present and there's no other derivatives, then the order is 1, or the first order. If you have something like dy on dx plus d squared y on dx squared equals, I don't know, e to the x, then because this is second order, this becomes a second order differential. Now, keep in mind, just because you have something like this, y dash squared equals x squared, whatever, right? This doesn't make it a second order differential. Because it's still just the first derivative, this is still first order. Okay, you definitely have to keep that in mind. What's another example of something? I guess you can probably imagine what third order would be. Maybe I'll chuck in another one actually. Like if I had d cubed y on dx squared plus, and then let's say d squared y on dx squared. Let's put a sine x next to this. This here would be third order because of this thingy. Fair enough. I feel like that's pretty easy. I don't know how that's tricky at all, really. But yeah, that's how we sort of deal with these. Now, of course, I've kind of thrown around different examples. We won't be dealing with things this sort of difficult. I don't think you'll deal with that till university. Um, Even second order, we won't really deal with second order where you have a dy dx and a d squared y on dx squared as two separate terms. The only sort of second orders we'd possibly deal with, whereas only a d squared y on dx squared equals something. Okay. So we'll be only really scratching the surface, but I guess that's good. Now we also have to talk about linear. Alrighty. A first order linear differential has to follow a particular form. In fact, the form is, so must follow the following form. dy on dx plus f of x times y equals g of x. Okay, this just sounds like gibberish, and I think it's overcomplicated for no reason. There's really two things you have to keep in mind, okay? This must be alone, like me. And this has to have power of 1. Okay, so the y has to have a power of 1. Now, I guess, yeah, that's kind of the case. But really, even you don't even have to have an f of x, like it could be a constant or something. So it's, yeah, okay. I think we'll go through some examples and tell me whether they are first order or second order first. And then afterwards, we'll go through some other questions and tell me whether it's a first order differential, whether the first order differential is linear or not. So let's go through this. dy on dx equals x plus y. Is this linear or not? Is this first order, second order, third order? I think we'd all say first order. Why? Because this is just the first derivative of x. Okay. The first derivative of y, rather. What about if you had dy on dx plus d squared y on dx squared equals x plus y? What's this going to be? It's going to be second order, right? Because it's there's a second derivative present. Second order. Okay. Now, for the following, can you tell me whether you think they are linear or non-linear? So let's go through this one. dy on dx equals x plus y. Linear or non-linear? Okay. Well, does it follow those two little conditions we have? I guess it does. The dy dx is on its own, and it's just the first order, so which is important. And then the y is just to the power of 1. Wonderful. So it seems like, yes, linear. Also, can you write it in another form? Yeah, you can. You can write it in the form that we discussed before. Dy on dx minus y equals x. You can see there is a function here. The function's just 1. And then you can see there is a function of x on this side. It's just x. So it abides by the condition, or the what's it called? The form that I've written above. Okay. How about dy on dx equals y squared? Linear or non-linear? Okay, I think we can say non-linear. Wonderful, wonderful. And what's the reason that it's non-linear? Because of the y squared must be 1. Okay, and the last one we'll do dy on dx equals x squared. No. Actually, wait, no, it is. Yes, this is linear. Why? Because even though there's no y term, that's okay. The y term is unnecessary because the function at the front could have been 0, right? All that we care about is that it's not a y squared, okay? Or an y in the denominator or something. That's the main point. This is still linear, okay? This is on its own, which is perfect. What about, I said we'll finish, but I think we'll do 2 more. Dy on dx. Actually, let's change this up a bit. Y dash equals y over x. Linear or non-linear? I think it's linear because y is still to the power of 1 and it's still dy dx on its own. Okay, so we haven't changed anything. This is, well, like we don't have a higher power of y or anything like that. But what if I go and I just rewrite it in a different form? What if or a different one? I say y dash equals x on y. Now you have y to the power of minus 1. And plus, if you try writing it in the other form, then I think you get it like this. Y dash minus x actually equals x. And then therefore the y dash isn't on its own. The y dash, when we say has to be alone, we mean that it shouldn't have a y next to it or a y function next to it. It can have x terms or x functions because you can just divide every term by that function and get rid of it. Okay. But if you have a y function there, then even if you divide by that y function, it's just not going to satisfy this form from above, wherever I've written it, because then you have some extra function of y, maybe even on the other side. Nice. Okay, now that we're sort of done with all of the mess or the tedious stuff, let's talk about the solutions to differentials. So without even realizing, you've sort of been doing this. Whenever you do integration, you're solving for the solutions to a differential, right? Like if I tell you dy dx, if I say solve dy dx equals 2x, what you're going to do is you're going to say, well, when I differentiate y, I get 2x. So to find y, I have to integrate. And that's why you would just say integral with respect to x, integral with respect to x, y equals the integral of 2x dx. Then of course this equals x squared plus c. There you go. Y equals x squared plus c. And what does the c refer to? Well, the c is that constant that moves it up or down. And I think you can sort of recognize that there's a whole family of functions that all satisfy the same differential. Okay, one's just a translation of the other. And that's something that I guess they like to mention in the textbook. There is a family of solutions to the same differential. Sometimes they don't have to kind of look the same. Okay, many things can satisfy the same the same differential. Actually, no, would they? Would many things have sign? I guess only if they differ by the constant. Maybe they look like they're in a different form, but in reality, you can simplify them or you can do a few arrangements and they come out to the same, effectively the same graph. Yeah, that's a better way of saying it. Okay. Now, sometimes questions can be asked like this. Are the following solutions to this differential? What's the differential? Let's probably should mention that. dy dx equals 3x. And let's have y here equals e to the power of 3x. And let's have here y equals 3 over 2 x squared. Have a go. Tell me if when you differentiate either of these two, it satisfies it. Okay, nice. So if you take the derivative of the first one, I think you get dy dx equals 3. So obviously no. And if you take the derivative of the second one, you get 3x. And then obviously yes, because it if you differentiate and it satisfies the differential, and there you go, it's a solution to the differential. Okay, how about this next question? Show that y equals sec x is a solution to dy on dx equals y square root of y squared minus 1. Have a go, take the derivative and see if you can sort of get to this. Recognize the fact that actually our differential is not written in terms of the independent variable x, it's written in terms of the dependent variable y. So maybe you need to do some sneaky manipulation. Remember some of our trig identities to replace some of those tan and secs with the y's again. Yeah, I don't know. Have a go. All right, unpause. Now, if y equals sec x, dy on dx is going to equal, what's the derivative of sec x? You should probably know this. It's sec x tan x. Yeah, imagine I said you should probably know this and I messed it up. That would be good to upload. Alrighty. Now, clearly it's written in terms of x's. We need to write it all in terms of y's. I think we can see that this sec x is clearly just the y from before. And what about this tan x? Well, if you didn't recognize this, make sure that you do, like sort of revise your year 11 trig identities. 1 plus tan squared x equals sec squared x. And therefore, tan x equals sec squared x minus 1. Maybe I should have mentioned something. We'll say for x's between pi on 2 and 0. My bad. That's a bit better. Now that I've mentioned this, I can differentiate between the differentiate. I can distinguish between the plus or the minus. Because my x's are between 0 and pi on 2, 10 is positive. So we should take the positive. And then therefore, this can be written as the square root of y squared minus 1. So now when we go to write out dy dx, it's going to be y square root of y squared minus 1. Obviously, the answer would have been different if we had mentioned maybe from minus pi on 2 to 0. Very nice. Okay. Now, of course, I'm going to give you, you can just solve your own differential equations, as I'll show you here. Solve, we can say the following. And what I'll do is I'll just chuck in some initial conditions for you as well. So dy on dx equals 6x squared minus 2x minus 3. And then we'll say goes through 0, 4. Okay, so have a go. I'll start writing in some more ones as well. Yep. Pause, have a go. I'm going to do them now. So to find y, you have to integrate this thingy. Which is 2x cubed minus x squared minus 3x plus c. When you sub in 0, you get 4. So therefore, y equals 2x cubed minus x squared minus 3x plus 4. Nice. For this next one, we need to integrate again to e to the 3x dx. When we integrate exponentials, we divide by the derivative of the power. So it's 2 on 3 e to the 3x plus c. And then when you sub in 0, you get 4. So 4 equals 2 over 3. E to the 0 is just 1. So plus c. C equals 4 minus 2 on 3, which is 10 on 3. Therefore, y equals. Very nice. What about this one? Yep, so have a go at that one and also have a go at this. This one as well. All right, I'll answer them now. So f of x is just going to equal the integral of sine of 3x dx, which is going to equal negative 1 on 3 cos 3x plus c. When you sub in pi, you get 2. So minus 1 on 3 cos of 3 pi. That's the same as cos of pi. Cos of pi is 0. No, minus 1. So this is plus a third plus c minus a third. So it's 5 over 3. Yes. Bruh, almost messed that up. Y equals minus 1 on 3 cos 3x plus 5 on 3. And then this one, we're going to just say y equals the integral. I'm going to take that 2 over 3 out because I just don't like writing it inside where everything else is. And then it's going to put a, yeah. 2 on 3 ln of the absolute of x plus c. And it says when x equals 1, y equals 2. Ln of 1 is 0, so that sacks off. And then we just get c equals 2. Of course, you would have to show this yourself. Nice. Just so you know, there's some other questions they could obviously write it something like this. Let me just chuck it in. Verify the general solution and then specify any parameters in this solution and state the required particular solution of solution said 4 times in this sentence of the initial value problem. The general solution, differential equation, and initial condition. So what it's saying is, first, we need to show that this thingy here satisfies this differential. If it satisfies this differential, pick out any of the parameters. I think the parameters are just A, okay? And then try and solve for A. That's basically it. Okay. Have a go. Have a go trying to find, showing that it's a solution to the differential. That is, when you differentiate this, you can get it into that form and then find the A and yeah, get back to me. All right, once you've done it. So dy on dx equals, we take the derivative of an exponential, you multiply by the derivative of the power. So it's minus 2a e to the minus 2x. Now, let's write this, because we need to get it in terms of y. Let's write this again here. And this whole a e to the minus 2x, you can tell is no longer there. So clearly we've subbed it out, probably by taking that 10 and moving it to the other side. And then this becomes minus 2, y minus 10. And then by just expanding the negative into it, you get to 10 minus y. Very nice. So therefore it satisfies the differential. And now because it satisfies the differential, we can find what the a is. By subbing in that, I think we get a as minus 7. Yep. Easy peasy. Okay, how about this question? It's similar, but there's a bit more to it, you know. This one's a second order differential because it's got the d squared y on dx squared. Have a go. Okay, once you've had a go, I will go through the solution. So first we need to show that the second derivative of this satisfies this. And then we need to find the a and the b. So dy, I say so too much. 2a cos 2x, then minus 2b sine 2x. Take the second derivative, and we get minus 4a sine 2x minus 4b cos 2x. Now, take out a negative, and negative 4, and you get a sine 2x plus b cos 2x. And I think you can see that that's just y, isn't it? It's the same thing. So d squared y on dx squared equals minus 4y. And then by just moving that over, we get d squared y on dx squared plus 4y equals 0. And therefore we've satisfied, or we've showed that this function y satisfies this second derivative, or this differential. And now we have to find the a and the b. Okay, so let's sub in 0, 1 into our y equation. So 1 equals, when you sub in 0 into the original, sine of 0 is 0, so that goes away. Then you just get b cos of 0 is 1. Oh, we found b. Oh, there we go. Let's go to the first derivative. When you sub in 0, you get 2. So 2 equals 2a cos of 0 is 1. So there we go. And then minus 2b, but then the sine of 0 is 0. So then that goes away. And therefore, we also get a equals 1. And now you can write it as a full thing. Yeah, very nice. I'll chuck in another one, because I think this one's going to get a bit harder. I don't know. Have a go. All right, once you've had a go, let me do this. dy on dx equals 2a e to the 2x minus a half. Clearly, this a e to the 2x has disappeared. So it seems like that's what we're going to be rearranging our y equation for and subbing into and replacing. So Um, ae to the 2x is y plus x on 2 plus 1 on 4. So now this is going to equal 2 y plus x on 2 plus 1 on 4 minus a half, which is 2y plus x plus a half minus a half is gone. And there we go. Wow, it wasn't that bad. And then the first one, we need to find what the a is. Let's just sub in 0, 0 minus a quarter. So I think it's 5 on 4. Yeah, a is 5 over 4. Why am I not writing? Not bad, right? Now, I think what you can tell so far is all of the differentials we've been trying to satisfy, or sorry, all of the original functions or the differentials we're trying to satisfy are quite easy. And sometimes if they're really difficult, they won't ask you to integrate your differential to get back up to the initial function. They might tell you, show that this function satisfies it. These aren't good examples because these were quite easy. One may say that you could have even integrated this and actually gotten something like that. Yeah. But we haven't covered that yet. In fact, we're going to cover it now. Okay, maybe actually even this we wouldn't have been able to solve just yet, but we will be able to now. So every time we've been doing integration, we've been always integrating. Say we have dy dx equals 3x. We've been integrating with respect to x. And of course, that kind of cancels off. And if you integrate, you get y, and then this is 3x squared over 2 plus c. But what if we were integrating and our function on the other side, so our integrand had a y in it? Okay, so let's see, how can I write this? Let's go to a new page. Solving differentials of the form dy on dx equals g of y. Now, how do we solve an integral of this form? Let's give ourselves an example and we'll sort of see how we run into a bit of an issue or how it's a bit different to ones from before. So let's say you had dy dx is equal to, and let's do y squared. Okay. Normally, we would say, oh, that means y equals the integral of whatever's on this side with respect to x. But how are we going to do this? Okay. Like, that doesn't make any sense. You can't integrate y with respect to x. So we need to rearrange it. We need to get it in a bit of a different form. So let's manipulate this. The way that I do questions like this is to take the reciprocal of both sides. So let me write that in. So what do you get now? You get dx on dy equals 1 over y squared. Now, I'm going to integrate both sides with respect to y. What happens when I integrate both sides with respect to y is this dy and this dy cancel, and I effectively, even though this is poor notation, it's a good way of thinking about it, this effectively becomes the integral of dx, and then this left-hand side just becomes like an easy breezy question, the integral of y to the minus 2 with respect to y, which I can evaluate because it's y's with respect to y. Now, what does my left-hand side go to? Well, the integral of dx is kind of like having an imaginary one there. Well, not imaginary, but having like a hidden one. So that just becomes x. And then this, you sort of just add 1 to the power, divide by the new power. So it becomes minus y to the minus 1, and then plus c. Okay. And then this becomes equal to minus plus c. And we've almost fully gotten it in the form that's required. You might say to me, why did you put the plus c on the right-hand side when you were integrating both sides? Why didn't you put it on both? Or why did you choose the right instead of the left? It doesn't actually matter, okay? Constants are constants. Let's say we have this, and they gave me some initial conditions, and I had to solve for c. If it was on the right-hand side, and let's give a hypothetical, let's say it's on the right-hand side, and I get c equals 2. If I put it on the left hand, if I originally put the plus c on the left-hand side, guess what I would have gotten my c to be? Minus 2. Because if I moved it to the other side, it would have been the 2. Okay. And if I put a c on both of them, I mean, that would be redundant. They'd cancel each other off. But if I put a plus c and then like a plus d, guess what? If you move them both to one side, they're going to both add up to the 2 on here. Or if you move them both to the left, they're both going to sum to minus 2. So who cares, right? That's it's not necessary. Just put on one of them and then you can deal with the rest. Like it won't matter. So obviously, whenever you do a question like this, you're never supposed to leave it in x equals form. You always need to write it back as if it's a function or back as if it's a y equals something. And as such, we have to just rearrange. So let me take this, move it to there, that, move it to there. And we get 1 on y equals minus x plus c. And then we'll do, the obvious. There you go. Not bad, right? Not bad at all. That's that. Yeah. So take the reciprocal and integrate with respect to y. That's the best way to do it. Maybe if you're kind of concerned about why I can just cancel off and integrate with respect to x, don't really worry about the maths behind this because it's not technically the best way to have written this form, but it sort of gets the job done. You could have also pretended as if it was just like maybe this just makes more sense to have it as dx on dy equals 1 on y squared. And you just know that when you integrate this, you're going to get back x because you're integrating with respect to y. And maybe you don't want to overthink it. But that's that. Nice. I'll give you a few more. I want you to sort of have a go. And yeah, make sure you write it as y equals. So let's say solve dy dx equals e to the y. And if you're really bothered, you can differentiate it or your solution and confirm that it satisfies this differential. So have a go at that one. And let me put in another one. Have a go. All right, once you've had a go, let's go through these. Let's sack this off for a moment. dy on dx equals e to the y. So take the reciprocal of both sides. dx on dy equals e to the minus y, or 1 on e to the y. Then integrate this side with respect to x, with respect to y, my bad, and integrate this side with respect to y. Those cancel, and you basically get the integral of 1 with respect to x, which just goes to x. And then when you integrate the right-hand side, it becomes minus e to the minus y plus c. Okay. And then let's move this x over. Or actually, let's move this thing over, move that over. And we get minus y equal, what am I doing? E to the minus y equals minus x plus c, or c minus x, and minus y equals ln of c minus x. And then therefore y equals negative ln of c minus x. Now, should I have put absolutes? Hmm. Well, if you differentiate the positive, does it still give you that? Differentiate the negative? Okay, well, maybe I should just put here instead minus ln of c minus x, where c minus x has to be greater than 0, and therefore x has to be less than c. There we go. I think that's a better way of writing it. Nice. And then the next one that we put in here, dy and dx equals y. Oh, we'll take the reciprocal. And wait, what am I doing? And let's move this over. X minus c equals ln absolute of y. And then therefore y equals e to the x minus c. Now, I just want to make a point here. If you leave it like this, I don't know if you'll lose a mark, but it's definitely not in the neatest form. It's in an unnecessarily ugly form. So I'm going to split this up and say it's e to the x times, we'll put on this side, e to the minus c. Now, c is a constant. It's a random constant, which you can evaluate. Isn't e to the power of negative c also another constant that you could just evaluate? Like in the end, let's say you found c to equal 3. Okay. You would just write it as e to the minus 3. Or let's say c was like, well, I guess what's my point? My point is there's no point in writing it now with e to the minus c. You may as well just write this. You may as well just make this a new constant a. And then say y equals a e to the x. Like that's so much neater, right? A is still a constant. And now you can evaluate for a. You don't actually have to go back and say, but a equaled e to the minus c. Who cares? That's the constant of the equation. Okay. So try and make your life easy by doing this. Even if you have like ln of c, just make that a because that's just the constant. Okay. So that's the premise. Do I have any other questions to give? Yeah, actually I do. How about this one? So find the solution to dy on dx equals 3y squared. And then we can say, goes through 1, 4. All right, have a go. Once you've had a go, let's go through this. Dy on dx equals 3y squared. That means that dx on dy, make sure you take the reciprocal of everything. It's 1 on 3y squared. Integrating both sides with respect to y, we get x equals 1 on 3. That was y to the minus 2. When you add 1 to the power and divide by the new power, you get minus, then y to the minus 1 plus c. Move that over, x minus c minus 1 on 3 y multiplied by negative. What am I doing? C minus x, and this becomes plus c. Let's actually write it how I had it before. 1 on 3y. And therefore, wait, is this an easier place to find my c? Okay, here's a good point. If I rearrange this and I make this 3y, or make this rather y equals 1 over and then 3c minus x, that's so much effort to now go and find c once I sub in the 1 and the 4. So maybe worth finding the C early on when it's in a neater form, and then finally rearranging and getting it into the final form where y equals. So I think let's hold off on this and find what the C is. So when x equals 1, y equals 4. So this is C minus 1 equals 1 on 12. And therefore C equals, what is this? 13 over 12. So therefore it becomes 13 on 12 minus x equals 1 on 3y. And that means y equals 1 over 3 times 13 over 12 minus x. And I think if I multiply this by 4, multiply that by 4, our life becomes easy. 3 times 4 is 12. 12 times 13 over 12 is 13. So it's going to look like that. Oh, yeah, there you go. Okay, nice. Perfect. I think that's the extent of kind of what I want you guys to do. Yeah, not bad. Alrighty. I think that should be the end of this video because it's going to get way too long.